Good afternoon, everyone. Welcome back to the second half of our conference. We hope you enjoyed the morning sessions and had a chance to grab some lunch. The second half of our conference. Let's dive back into our enjoyed the morning exciting lineup of chance and grab sessions. The second half of our conference. Let's dive back into our enjoyed the morning exciting lineup of chance and grab sessions. The second half of our conference. Let's dive back into our enjoyed the morning exciting lineup of chance and grab sessions. The second half of our conference. Let's dive back into our enjoyed the morning exciting lineup of chance and grab sessions. The second half of
Ladies and gentlemen, esteemed guests and fellow academicians, it is our pleasure to welcome Dr. G. Ramya, Associate Professor in the Department of Mathematics at PVKK Institute of Technology. Dr. Ramya academic excellence is evident in her impressive educational background, having earned her MPhil, BH, and PhD in mathematics. Her doctoral thesis focusing on algebraic and structural properties of the product maximal graph and computation of the distance-based topology showcases her expertise in algebra and graph theory. With over 8 years of teaching experience and 6 years of research experience, Dr. Ramya has established herself as a dedicated educator and researcher. Her research interests lie in algebra and graph theory, and she has demonstrated proficiency in LaTeX and MATLAB software. We are honored to have Dr. Ramya with us today, and we look forward to her valuable insights and contributions. Please join me in giving a warm welcome to Dr. G. Ramya. And contributions. Please join me in giving a warm welcome to Dr. G.
Thank you so much, ma'am.
And contributions. Please join me in giving a warm welcome to Dr. G.
Thank you so much. Thank you, Menaka madam. Sorry, Menaka madam and Kritika madam. Thank you, Menaka madam. Shall we start, ma'am? Menaka madam and Kritika madam.
Yes, ma'am. You can proceed.
Okay. Thank you, Menaka madam. Shall we start, ma'am? Menaka madam and Kritika madam.
Yes, ma'am. You can proceed.
Okay. Thank you, Menaka madam. Shall we start, ma'am? Menaka madam and Kritika madam.
Yes, ma'am. You can proceed.
Okay. Thank you, Menaka madam. Shall we start? My screen was visible?
Yes, ma'am. Yeah, yes, ma'am. Visible only.
Okay. Thank you so much. My screen was visible? So good afternoon to everyone present here. I'm delighted to be a part of this national conference on recent trends in pure and applied mathematics. And first of all, thanks to Kritika madam for your kind introduction. I truly appreciate your warm words, ma'am. And also it is a pleasure to be here today and to share my thoughts on algebraic graph theory. And these are the today's content I'm going to discuss. First one, graph theory. In graph theory, the most important topic topics related to algebraic graph theory I discussed here. Then algebraic graph theory. In algebraic graph theory, I'm going to discuss how to draw a graph from group theory and also ring theory. And next one, product maximal graph. It is basically from ring theory, and some results also discussed to be here. And next, current scenario of algebraic graph theory, and next one, conclusion. So to begins with, let's take a step back and understand the foundation of our discussion. So graph theory is a powerful mathematical tool and understand the foundation of our discussion. So graph theory is a powerful did you hear me, ma'am? Tool and understand the foundation of our discussion.
Yeah, yes, ma'am.
So graph theory.
Your video is not visible. Your screen is visible, ma'am.
This one. Now the PPT was visible or not?
Yeah, PPT is visible. Screen is
Oh,
visible,
just a
ma'am.
minute. This one. Now the PPT was visible or not?
Yeah, PPT is visible. Screen is visible,
Oh, just a
ma'am.
minute. This one. Now the PPT was visible or not?
Yeah, PPT is visible. Screen is visible,
Oh, just a
ma'am.
minute. This one. Now the PPT was visible or not?
Yeah, PPT is visible. Screen is visible,
Oh, just a minute. This one. Now the PPT was visible or not?
yeah, PPT is visible. Screen is visible,
Oh, just a minute. This one. Now the PPT was visible or not? Sorry for the trouble. Okay. So first, introduction of graph theory. So graph theory is a powerful mathematical tool used to model relationships and structure. So when combined with algebra, it opens up new perspective for analysis and problem solving. So in this talk, we will explore how algebraic structure can be translated into graphs, and how this interplay enhances our understanding of both fields. So let us first start up the understanding of basics of graph theory and its significance. So a graph is a mathematical structure used to model relationships between the objects, and it contains set of vertices and set of edges and connected between them. So for example, you can think a social network where each person is considered as a node and the friendship between two peoples is an edges. And similarly, you have to consider a city map. Intersection can be the node and the road connecting between them is considered as the edges. Okay, so this is the simple structure allows us to represent and analyze various real world system effectively. And graph theory is not just an abstract concept, it plays a crucial role in many real world applications like computer science, artificial intelligence, engineering, and networks, etc. So, what makes graph theory even more fascinating is its connections with algebra. By applying algebraic structure, we can explore deeper properties of graphs, leading to new discoveries in cryptography, quantum computing, and optimization. And next one, the graphs come in various forms depending on how the vertices and edges are structured. So let's see some of the most common types of graph theory here. First one, undirected graph. So it is the edges having no direction in this graph. So the connection between two vertices are mutual. So for example, you have to consider the road network. If the road allows to travel in both directions, that is the best example for this undirected graph. So obviously for the directed graph, you have to consider a one-way road and follow a relationships on social media. So one person follows the other, but the reverse may not be true. That's why in a direction, the edges having some directions in directed graph. And next one, weighted graph. In weighted graph, edges having weights. That means they are giving some values of them. For instance, in a transportation network, the edges can be weighted representing sometimes distance or sometimes time or cost. And next one, simple graph. So it is the most
Yeah, yeah.
types, and it consists of set of vertices and set of edges with
Seller.
loops and no multi edges between the same.
24 KSM.
For example, imagine a friendship network where each person is connected to other. through a single directed link. Okay, and next one, multigraphs. So multigraphs means it allows a multi-edges between the same pair of vertices, and these are useful in modeling transportation networks where multiple routes exist between two locations. And next one, it is very important, connected graphs and disconnected graphs. So connected graphs is there is a path between every pair of vertices in the graph. So for example, in a fully linked social network, everyone can reach each other through some connections. And it disconnected means some groups in social medias there is no connections exist between them. So that is an example for disconnected graph. And some special graphs is also there. First one, bipartite graphs. The set of vertices in this graph, the set of vertices can be divided into two groups. The edges connects only from different groups. So the classical example for this bipartite graph is the job matching system. So you have to consider one set of people can be considered as a job seeker, and the other represents the job positions. So the edges between these two are a suitable matches. Okay, and next one, regular graph. A regular graph is a vertex has the same degree. And next one, planar graph. A planar graph is you have to draw a graph on a plane without edges or crossing. And next one, graph representation. First one, adjacency matrix. The adjacency matrix is a simple and fundamental way to represent a graph mathematically. So see, this is the example for adjacency matrix. Here I am giving a C4 graph, and there is adjacency between 0 to 1, 1 to 2, 2 to 3, and 3 to 0. So in this matrix, you have to consider how many vertices are there. So it contains that number of rows and that number of columns. The first one is considered as 0 row and 0 column. Second one is first row and first column. Second one, second row and second column. And the vertices are mentioned here. If the two vertices are adjacent, then you have to put here 1. Otherwise, 0. That is the meaning of this adjacency matrix. And next one, degree. It is basically a diagonal matrix. It is nothing but the degree of every vertex. So what is mean by degree? How many number of edges incident to that vertex is called the degree. So in this vertex 0, how many number of edges are incident? 2 edges are incident. So the degree of the 0 is 2. So likewise, the degree of every vertex is 2. And next one, Laplacian matrix. It is the key matrix in spectral graph theory, defined in a difference between the degree and adjacency matrix. And next one, graph coloring. It is a very interesting topic in graph theory. Basically, coloring is something we see everywhere, right? In the real world, in a real world, we can see everywhere coloring. For best example is mapping, world map, or scheduling, even in Sudoku questions also. But how does it works in a graph? That is the beauty of this graph coloring. Okay, so basically, graph coloring is the process of assigning colors to the vertices of a graph while following some specific rule. So the most common type in vertex coloring is no two adjacent vertices shares the same color. But we also have edge coloring, face coloring, and even total coloring is also there. Okay, so for better understanding, let's take an example. Imagine you have a map of different countries, right? So we want to color each countries such that no two neighboring countries have the same color. So that is exactly what to the graph theory. Okay, so here the two main topics is there, chromatic number and chromatic index. Here I discussing chromatic number. So it is nothing but the minimum number of colors needed to be properly coloring a graph. That is chromatic number. I gave one example here. You consider this C4. So in C4, I'm using a minimum number of color is 2, only green color and red color, because no two adjacent vertices are giving a same color. So that is adjacency between this green and red color. Therefore, I didn't give the same color. But see here, this green and this green are not adjacent. That's why I'm giving a same color. So similarly, for the graph, we need minimum 3 colors for coloring. In general, a complex of a graph is more color if we need 3 colors, right? So one of the most famous results in this thing is the 4-color conjecture, which says that any planar graphs, such as we have to consider a world map, can be colored at least four colors, at most four colors. So this theorems took over 100 years to prove and was one of the first major mathematical proofs done using computers. So therefore, graph coloring is a powerful tool in graph theory, helping us solving problems in scheduling, networking, and etc. And next one, graph labeling. While graph coloring is assigning a color, right? And labeling assigns the numbers in a graph elements in a structured way. It is a process of assigning numbers to the vertices, edges, or both. Some specific rule is also there. You have to, I will give one example here. Think an address system in a city. So houses on one side of a road have an even number and those on the other side have an odd number. So this is the structured numbering helps in navigation. I will give a basic definitions of labeling, that is called graceful labeling, etc. And next one, domination number. And domination number is one of the interesting topics in graph theory. Okay, it is a fundamental topic also that deals with selecting a subset of vertices such that every vertex in a graph is either in a subset or adjacent at least one vertex in it. So you just, I will give a two real life example here. Okay, you just imagine you are a ruler of a kingdom, right? So you want to place a god in a certain city so that every city is either protected by a god or has a god stationed in it. So that is, and here the main condition is minimum number of god we need to use to sure that every cities can be covered. That is a domination number. Okay, so the next best example is for recent trending mode called influence game in social network. Okay, so you just imagine influencer on social media and you want to spread a message to people as possible, but instead of messaging to each and every people, you can choose some few specific people who will spread it for you. So here the question is, what is the smallest number of influencer you need to ensure everyone gets the message? So that's exactly the domination number is. Okay, and this influencer are your dominating set and you are trying to find the smallest group that ensure every problems in a network is either an influencer or followers one. So this is the definitions of dominating sets and minimal dominating sets and what is the domination number. Okay, and the next topic is algebraic graph theory. So first one, introduction. In introduction I will give and the next topic is algebraic graph theory. So first one, introduction. One of the most famous graphs in algebraic graph theory is a Haley graph. Okay, so it is started from 1878. It explores, basically algebraic graph theory explores the relationships between the graph theory and algebra, primarily using matrix representation. And this algebraic approaches allows us to study the properties such as connectivity, symmetry, spectral characteristics of graphs with mathematical precision. So the technique of algebraic graph theory are widely used in network sciences and even physics also. So understanding the algebraic properties of graphs helps us to optimize the network and development efficient algorithms in various real-world applications. And next one, significance of algebraic graph theory. Let's say you have a big and complicated networks. Maybe you have to consider a social network or a road system or even a molecule. Right? How do we analyze it? Instead of just looking at as a dot and lines, algebraic graph theory gives us a mathematical way to study these networks. And using algebra to understand the graphs, first one, and normally we think a graph as a picture. But algebraic graph theory let us represent them using numbers, equations, and matrices. And this helps us analyze large and complex graphs quickly without having to draw them out. And in algebraic graph theory, eigenvalues plays a vital role. So imagine you want to know how well connected the network is. So like how fast our news can be spreaded on a social media. By using eigenvalues, we can measure the connectivity, stability, and even detect a fake news networks also. And sometimes the two graphs are looking different, but actually it is in the same structure. Instead of checking them manually, algebraic graph theory helps us compare the graphs using mathematical fingerprints like eigenvalues and automorphism groups. And applications in real life is the social networks, cyber security, and quantum computing also. And these are the conclusions of algebraic graph theory. And the main thing is, and these are some conclusions of algebraic sorry. Here, some famous graphs in algebraic structure. One of the most famous way to build a graphs from groups is by Haley graphs. It is named by Haley in 1878. If you give me a group and set of generators, I can able to build a graph. Build a Haley graphs. In a Haley graph, the vertices are considered as a set of all elements in a group G, and the edges are connects the elements based on the multiplications with generators. And this Haley graphs is widely used in studying about symmetry, automata theory, and even network topology. And next one, another graphs from groups is a commuting graph, which comes from the non-abelian group. And you have to consider the vertices set of all elements in a group G. And if two vertices are adjacent in a commuting graph, if they commute each other. Okay, and it helps to analyze the commutativity structure of a group. And actually, the first major graphs in algebraic graph theory was Jordan graph. It is introduced by Jordan in 1869. It arose for permutation groups and was used to study the group action and automorphism. And this graph laid the foundation for studying group structure using graphs. And later on, Haley graphs, Bossert graphs expanded this idea and leading to the deeper results in combinatorial theory. And next one, vertex order graph. And the vertex order graph was introduced by Kalamani and Kritika in 2019 to study the cyclic group using graph theory. And in this graph, the vertices are represented the elements of the finite cyclic group, and two vertices are connected if they have a same order in the group. Okay, since different elements can have a different order basically, so the graph is often disconnected with each connected components consisting of elements with the same order. And this graphical representation helps in understanding the structure of cyclic group and in a visual and mathematical way. It also has an application in molecular graph theory also. Additionally, its complemental graph has been explored to analyze further combinatorial properties. I gave here one example of vertex order graph Z9. Basically, vertex order graph is a disconnected graph. Okay, and next one, zero divisor graph. From now onwards, I'm going to show you how the graph can be drawn from the group. And just like group, we can construct the graphs from ring group. So let's look at the sum of the key graph associated with ring group. First one, zero divisor graph. It is introduced by Beck in 1988. And later on, Anderson and Livingston was developed this zero divisor graph. And in a zero divisor graph, the set of all vertices can be considered as a non-zero zero divisor. And the edges between the two vertices is the product of that two vertices is equals to 0. I gave one example here. See, integer modulo 6. I consider the integer modulo 6. The set of all elements in R is 0 to 5. What are the vertices in a zero divisor graph? It is a set of all non-zero zero divisor. So I have to put 2, 3 and 4. Okay, two vertices are adjacent if and only if the product of two vertices equals to 0. So consider 2 into 3, that is equal to 6, that is also equal to 0 value. That is adjacency between 2 and 3. Similarly, 3 and 4 equals to 12, that is becomes also 0. So that is adjacency between 3 and 4. But unfortunately, the product of 2 and 4 is equal to 8, that belongs to 2. So that there is no adjacency between 2 and 4. Okay, and next one, total graph, and this total graph was introduced by Anderson in 1999. And here the set of all vertices is considered as the set of all elements in a ring R, and two elements are connected if their sum is in a zero divisor set. Okay, and let's enter into the new topic called product maximal graph. So here now we see many graphs like Haley graph, Coset graph, zero divisor graph, etc. So by inspired by these graphs, we introduced a new concept in 2021, which focused on a different multiplicative behaviors in a ring. So that graph is called a product maximal graph. So before we define a product maximal graph, it is important to understand the fundamental concept in ring theory. So a maximal ideal is a special proper subset of ring. Okay, so this is a maximal ideal. We need to know what is maximal ideal. That is a basic definition of to draw this product maximal graph. Okay, so what is the maximal ideal? So there is no bigger ideal between the maximal ideal and the whole ring R. Okay, so now we defined our new graph, product maximal graph. Here, R is a set of all finite commutative ring with unity, and you have to consider the maximal ideal M1 to MR. Okay, so the set of all vertices in a product maximal graph is whole elements in R. And if two vertices are adjacent, if and only if their product is belongs to the maximal ideal, then there is adjacency between X and Y. Right? So this is called the product maximal graph. For better understanding the product maximal graph, let's take an example. So this is called the product maximal graph. See here, I will give one example here. Integer modulo 6. Right? So I will explain this in a step-by-step mode. First, you have to identify the maximal ideal of Z6. Right? So what are the maximal ideal of Z6? M1 0 2 4, it is generated by 2, and M2 0 3, it is generated by 3. Now you have to define the vertex set. So these are the vertex set. Set of all elements in R is considered as a vertex in a graph. So 0 to 5, I place it here and establish the adjacency now. So what is the product of 1 and 2? That is equal to 2, that is belongs to the maximal ideal. And 2 3, that is equal to 6, belongs to 0. 0 is also in the maximal ideal, and similarly everything is adjacent to all other. But see here, there is no adjacency between 1 and 5, because the product of 1 and 5 equals to 5, that is not in the maximal ideal. So there is no adjacency between 1 and 5. Okay, next we will see the some basic results of product maximal graphs. Yeah, the first one, degree of the vertex. In a product maximal graph, it can be built using maximal ideal of finite commutative ring. Okay, so I will explain by using this graph only. First, you have to consider there are two types of vertex set here. One set of vertex that belongs to the maximal ideal, and other set of vertex that does not belongs to the maximal ideal. Here you have to consider 0, 2, 3 and 4 belongs to the maximal ideal, and remaining 1 and 5 are does not belongs to the maximal ideal. So it forms two different sets, right? So first you have to consider a vertex that belongs to the maximal ideal. So see here, that belongs to the maximal ideal 2. 2 is adjacent to all the vertex, all the remaining vertex in the graph. So 2 is adjacent to 1, 2 is adjacent to 0, 2 is adjacent to 5, 2 is adjacent to 4, and 2 is adjacent to 3. So similarly, the set of all elements in a maximal ideal is adjacent to all other vertex in the graph. That's why the degree of the vertex belongs to the maximal ideal. V belongs to Mi means what is the degree? N minus 1. Okay, so what about the remaining vertices that does not belongs to the maximal ideal? 1 and 5. So look it carefully. This 1 is adjacent to only with the elements of maximal ideal. 1 is adjacent to 2, 1 is adjacent to 0, 1 is adjacent to 3, and 1 is adjacent to 4. So the elements which are not in the maximal ideal, it is adjacent to only with maximal ideal. So here number of maximal ideal is I denoted here small m. That's why V does not belongs to maximal ideal, and the degree of that that vertex is m here. Okay, and next one, coloring. I already discussed about what is coloring. Here, chromatic number. So chromatic number means what? The minimum number of colors required to properly color the vertices of the graphs so that no adjacent vertices shares the same color. Okay, so similarly chromatic index also. Chromatic number is you have to color the vertex, and chromatic index means you have to color the edges, right? So the same, similarly, the number of edges colored by the same color, and no two adjacent edges shares the same color, that is called chromatic index. I gave the results of chromatic number and chromatic index. Chromatic number of the product maximal graph is m plus 1. So see here, I will give one example. This is a better example to understand here. So this is a unique ideal. It is a unique maximal ideal. So Z9, integer modulo 9. So what are the maximal ideal? 0, 3 and 6. So see the graph clearly. 0, 3 and 6 is adjacent to each other. So we can't able to give a same color for these vertex. But 1, 2, 3, 4, 5, 7 and 8 are not adjacent. That's why I gave a same color for these vertex. But this 1, 2, 4, 5, 7 and 8 are adjacent to remaining 3 vertex. No, that's why I didn't give the same color like this. So therefore, the chromatic number of the product maximal graph is m plus 1. And the next one, chromatic index. So chromatic index is nothing but you have to color the edges with some certain conditions. So chromatic index of the product maximal graph is n minus 1. This means that you have to properly color the edges. So I gave one example for chromatic index. This is the example for chromatic index. I mentioned here how many number of edges are colored with the same color. I mentioned clearly here. Okay, and next one, connectivity. So what is connectivity? So it is a set of vertices. The minimum number of vertices we need to remove from the graph, then the graphs become disconnected. So some set of vertices you are removing from the graph, then the graph becomes disconnected, and that set of vertices can be considered as a vertex connectivity. Okay, and sometimes the graphs become trivial also. What does mean by trivial? It reduces the single vertex. Okay, so next, this is the result for the product maximal graph. The vertex connectivity depends on the structure of the maximal ideal. If you, I will give here, see this example. 0 is connected to all other vertex, and 3 is connected to all other vertex, and 6 is connected to all other vertex. If suppose you have to consider the set of vertex 0, 3 and 6, you have to remove this from the graph. What it happens? The remaining vertices 1, 2, 4, 5, 7, 8 are disconnected, and it becomes isolated, single vertex. That's why the vertex connectivity of the product maximal graph is m. What is mean by m? M is the number of elements in the maximal ideal. If you are removing this m elements from the the product maximal graphs become disconnected. And next one, edge connectivity. So edge connectivity is similar to the vertex connectivity. If you are removing some edges from the graphs become disconnected. Okay, so here the product maximal edge connectivity of the product maximal graph is also m here. Okay, if you are removing m number of edges from the graphs become disconnected. So finally, we observed one thing from from vertex connectivity and from edge connectivity, and minimum degrees are equal in the product maximal graph. Okay, and from edge connectivity. And next one, matching number, click number, independence number of the product maximal graph. So first one, I will discuss what is mean by independent set. A set of vertices is said to be independent if no two vertices in the set are adjacent. And what is independence number? Independence number is the size of the largest independent set in the graph. Okay, so we will discuss what is the independence number of the product maximal graph. You see this theorem number 6. Any vertex inside the maximal ideal is always adjacent to the any other vertex. So basically, in a product maximal graph, set of all elements which are in the maximal ideal is adjacent to all other vertex, and the remaining vertex which are not in the maximal ideal is adjacent to only with the maximal ideal. It is not adjacent to itself. Right. So using this condition, I have to prove here as a dependence number is n minus m. So any vertex inside the maximal ideal, so that cannot form the independent set, right? So basically, a set of all elements which are in the maximal ideal forms a complete graph in a product maximal graph. Okay, in a product maximal graph, it forms a complete. So we have to consider outside the maximal ideal, the only connected to some ideal elements, but not necessarily to each other. So the largest independent set consists of the vertex outside the maximal ideal. So it is unconnected themselves. So the independence number of the product maximal graph is n minus m. And next one, click number. So basically, it is also the subgraph of the main graph, but that subgraph becomes complete. So that set is called click number. Okay, and see, this is the theorem of click number of the product maximal graph. Theorem number 8. The click number of the product maximal graph is m plus 1. How to prove this? And all the elements inside the maximal ideals forms a click because their products is also belongs to the maximal ideal. So at least, and this, so m, here m plus 1, no? So here m is, you have to prove set of all elements which are in the maximal ideal forms a complete subgraph. So m. What is this plus 1? You have to consider one vertex from the non-maximal ideal. Okay, so obviously non-maximal ideal is adjacent to every elements in the maximal ideal. So obviously it forms a complete graph. Okay, and next one, matching number. You have to know what is meant by matching number. A matching number is nothing but it is a common vertex set. Okay, so this is the theorem of matching number. First, we need to understand what is matching, independent edges, maximum matching, and perfect matching. We need to understand those things. Okay, I gave here definition of matching number and definition of maximum matching. What is independent edges? Independent edges is nothing but no two edges shares the common vertex. And what about maximum matching? Maximum matching is refers to the largest possible matchings in the graph. And the main topic is perfect matching. The perfect matching is if you are consider even number of vertices. If 2, 3, 2, 4, 6, 8, like even number of vertices, there exists a matching that covers all the vertices. That is called perfect matching. So our product maximal graph is also a perfect matching in one condition, right? So this is the theorem. Theorem number 7 is a matching number of the product maximal graph. If you have to consider n is even, even means z6, maybe z8 or z10, even n is even, then the matching is n by 2, and if n is odd, that is the matching is m. So see, I gave example for both even numbers and odd numbers. Here I considered integer modulo 8. So what are the maximal ideals? Here the maximal ideal, we no need to worry about the maximal ideal. You have to draw the product maximal graph. So what is matching number? The edges can share at least a different pair of vertices. So see here, I pop up the blue color, that is a set of maximal ideal, maximum matching. So the 0, 1, 2, 7, 3, 6, and 4 and 5. So it covers all the vertices in the graph. And here I gave one example for odd numbers. The maximum matching of Z9 is 3 here. So apart from this blue line, you need not, so you does not able to, you are not able to select any edges apart from this. And next one, vertex covering. So vertex covering is the set of vertices that touches every edges in a graph. That is called vertex covering. This means that if you pick this set, every edges must have at least one of its endpoints in it. Okay, so for example, you have to imagine a road containing city. So a vertex cover would be the set of cities, and every road has at least one cities from it. Okay, that is the best example. And similarly, edge covering is also there. Edge covering is also the set of edges that touches every vertex in a graph. So in a simple word, we pick up n of edges so that no vertex is left over. And going back to the road network example, an edge covers would be a set of roads that ensures every city is connected to at least one other cities. And there is a famous proposition is there. It is introduced by Donald B. West. That is, independent set and matching number is equals to n. And similarly, independent edges and maximum edge covering is equals to n. This alpha is considered as independent number, and alpha dash is considered as a independent edges, and beta of g is considered as a vertex cover, and beta dash of g is considered as a edge cover. So the sum of these two is equals to n, and sum of the edge covering and the independent edges is equals to n. By using these two prepositions, I proved the edge covering and vertex covering of the product maximal graph. So vertex covering of the product maximal graph is m, and the edge covering of the product maximal graph is n by 2 if n is even, and n minus m if n is odd. I gave here one huge example for integer modulo z12. Okay, so here I pop up the vertices and some pop up edges. So that pop up vertices is considered as a vertex covering, because you have to consider these vertex. It must contains all the edges or one side of the edges, and the edges also cover every vertex in the graph. Okay, and this is example. And the next one, it is a Hamiltonian path. It is very interesting topic in graph theory. And what is mean by Hamiltonian path? So path that visit every vertex exactly once. If we need to find such a path in a graph, we say the graph has a Hamiltonian path. Now, if this path forms a cycle sometimes, so meaning it is starts, what is mean by cycle? The starting and the ending vertex has the same, right? While visiting, and also in a Hamiltonian cycle, every vertex must visit exactly once. That cycle is called Hamiltonian cycle. Once a graph contains a Hamiltonian cycle, then that graph is called a Hamiltonian graph. Okay, so you just think, I will give one example. Think a traveler who wants to visit every city exactly once and return to the starting city. If there is a way to do using this given road, then the network forms a Hamiltonian cycle. And and this idea is widely used in real world applications, right? Route planning, optimization problem, and even computer network designs also. So what about our product maximal graph? If our product maximal graph is a Hamiltonian or not? Yes, it is Hamiltonian if n is even. So see here, I gave an example here, Z6. This the maximal ideal is 2 and 3, and set of all maximal ideal is 4. The number of elements in a maximal ideal is 4, and number of elements in non-maximal ideal is 2. Right? So if the starting point is 0, I gave a path here, 0 to 1, 0 to 1, that's a path, and 1 to 2, yes, there is a path, and 2 to 3, 3 to 4, and 4 to 5, and 4 to 5. I missed here to draw a red color line. So here also red color is happening. So there is, every vertex has joined exactly once, and also there is adjacency between 5 and 0. So it is a Hamiltonian cycle also. So there is a path, Hamiltonian path is also there, and it is a Hamiltonian cycle is also containing in Z6. Therefore, this Z6 graph is a Hamiltonian graph. And see this example, if n is odd, it is not a Hamiltonian cycle. Okay, I pop up here in the blue color line. You have to start with 1, 1 to 0, 0 to 2, 2 to 3, 3 to 4, 4 to 6, and 6 to 5. But 7 and 8 are does not cover. So what is the condition? You must cover all the vertices in your graph with exactly 1. So it's not able to cover the 7 and 8. This is not a Hamiltonian path, and also there is no adjacency between 5 and 1. We are starting from 1, no? So it's ending with 5. So there is no adjacency between 5 and 1. Therefore, this is not a Hamiltonian cycle, and this Z9 is not a Hamiltonian graph. Okay, and next one, planar graph. Planar graph that can be drawn on a plane without any edges can be crossed. Okay, so this means that we can arrange the vertices and edges in a such a way that no two edges overlapping except at the vertices where they meet. Okay, example, imagine a road map. You just imagine a road map cannot connect different cities by vertices. So if your road can be drawn on a flat surface without crossing each edges, then that map represents the planar graph, right? So here, our product maximal graph is planar or not? Yes, it is planar, but there is some condition that if n is less than or equal to 4, number of vertices is less than or equal to 4, then our product maximal graph is also planar. Apart from that, not able to draw this graph without crossing edges. Okay, and these are my references of algebraic graph theory. It is very important references about books, and some research papers is also there, and these are my papers. And next one, current scenario of algebraic graph theory. Algebraic graph theory is an existing field where algebraic structures like group, rings, and matrix helps to analyze the graphs beyond their visual representation. So today's fastest world, algebraic graph theory is widely used in spectral graph theory, where eigenvalues reveals the graph connectivity, expansion properties, and robustness. It also plays a key role in network sciences, optimizing everything for social networks to blockchain security and even cryptographic protocols. So beyond the networks, algebraic graph theory gives applications in chemistry through topological indices, helping to predict molecular stability and an artificial intelligence, where graph-based learning enhances deep learning model with emerging fields like quantum computing and graph-based artificial intelligence. Algebraic graph theory is rapidly evolving, bridges pure mathematics with cutting-edge technology. And so conclusion of my topic is the product maximal graphs helps to understand the important properties like connectivity, coloring, matching, independence numbers through the algebraic approach. It shows how algebra and graph theory comes together to solve the real world problem, especially in networks. So I hope this talk have give you a new insight and ideas for future explorations. Thank you for all your patience and for being a wonderful audience. And if you have any questions or thoughts to discuss, I would be happy to answer them. Thank you so much. And if you have any questions or thoughts to discuss, I would be happy to answer them.
Dear
Thank
participants,
you
if
so
you have
much.
any questions, you can ask. Now, question session.
Ma'am, I have one question, ma'am.
Yes, ma'am.
Dear participants,
Ma'am,
if you
is
have
there
any
any
questions, you can
symmetric
ask.
condition exist
Now,
for
question
adjacent
session.
matrix, ma'am? Ma'am, I
Symmetric,
have one
yes,
question,
ma'am. It is
ma'am.
obviously it is a symmetric matrix
Ma'am,
only,
is there
no,
any
because the
symmetric
rows and
condition
columns are
exist for
considered
adjacent
as a
matrix, ma'am?
vertices. So obviously it forms a symmetric matrix. Every adjacency matrix, if you are drawing a, if you are writing adjacency matrix for a graph, it obviously creates a symmetric matrix.
Yeah, ma'am. Thank you, ma'am. But the directed graph and undirected graph will be same or not, ma'am?
No, directed graph and undirected graph are
Yeah,
both
ma'am.
are
Thank you, ma'am.
different.
But the
In a
directed graph and
directed graph,
undirected
it
graph will
forms a
be
symmetric matrix.
same or
But
not, ma'am?
sorry, in an undirected graph, it forms a symmetric
Yeah,
matrix.
ma'am. Thank you, ma'am.
But in
But
a
the
directed graph, it is in
directed
somewhat
graph,
other
it forms
some other way,
same or
because
not,
degree
ma'am?
in degree out is there, no. So there is
Yeah, ma'am.
the matrix will be different.
Yeah, ma'am. Thank you, ma'am.
It's okay. Because degree in degree out is there, no. So there is
Yeah, ma'am.
the matrix will be different.
Yeah, ma'am. Thank you, ma'am.
It's okay.
Yeah, ma'am.
Any
Ma'am,
other
I have
questions?
another doubt, ma'am.
Yes, ma'am.
Ma'am, what is the purpose to make
Any other
algebra
question?
and graph theory combines, ma'am?
Ma'am, it is a really
What is
real
the
world
purpose
application is a
to
really heavy one.
make
First, you have
algebra
example. I
and
will give
graph
you an
theory
example. I'm
combines,
also
ma'am?
working in that topic. I'm working in a chemical
What is the
molecules,
purpose
like
to
you know that
make
atom bonding is there,
algebra
no?
and graph
So
theory
the
combines,
structure
ma'am?
is like this some if you are draw a graph from algebra, the most of the graphs are related to that molecules. So we can able to find the chemical atom bonding relationships using in a mathematics way. So there is a very real world application is there, ma'am. If you are draw a graph from algebra, it is useful to many fields from AI and even atom molecules like that, ma'am. Many
Yeah,
real
ma'am.
world
Thank you so much, ma'am.
fields from AI and even atom nowadays this algebraic graph theory was well developed because of
Yeah,
real
ma'am.
world
Thank you so much,
applications.
ma'am.
And even nowadays topological indices in finding a atom bonding, it is very
Yeah, ma'am.
important,
Thank you so
very
much, ma'am.
useful for that. Even nowadays topological indices in finding a atom bonding, it is very
Yeah, ma'am.
important,
Thank you so
very
much, ma'am.
useful for that. Even nowadays topological indices in finding a atom
Any other
bonding, it is
questions?
very important, very useful for that.
Madam, I have one doubt, madam.
Yes, ma'am.
Madam, complete
Any other
graphs and
questions?
uncomplete graphs. Which
Yes,
software we
ma'am.
have to draw, madam? Complete
Any
graphs.
other
Which
questions?
software we have to
Uh,
draw the graphs, madam?
Madam, which typesetting you are using, madam? Latex or Word, madam?
Word,
Madam,
madam. Actually, I am learning latex, madam. Some
latex is best one for drawing a graph. If you are using latex means
word,
the
madam.
GeoGebra,
Actually, I am learning latex, madam.
GeoGebra. GeoGebra is the best to draw a graph. It is very easy and understandable, and you just copy that graph and place it in a latex. It is automatically created the coding. We no need to write any codings in latex.
Okay,
Latex is
madam.
better to write a coding.
Okay, madam. Okay, madam. Thank you, madam.
It's okay.
Excellent, madam, your presentation.
Thank you so much, ma'am.
Really,
Thank you.
madam, very useful to, very
Thank you.
useful.
It's okay.
I am
Thank you.
also a graph theory
Okay.
research scholar,
Thank you so
madam,
much, ma'am.
in Yogi Vemana University.
Okay.
I have a lot of confuses there, madam. Somebody says
Okay.
in MATLAB you have to use. Someone
No,
says
madam.
a lot
MATLAB
of
is only for
confuses
calculating
there.
the topic. You are
Somebody
it's
says
you need
in
to
MATLAB
draw
you
and
have to
present a
use.
paper means
Someone says
you need to publish a paper means you just go with latex and GeoGebra.
okay, madam.
Need to draw and present a paper
Madam, I
means
have one
MATLAB is
request, madam.
yes, ma'am. You just go
Uh,
with latex
if
and
any day
GeoGebra.
I have some doubts. Can you
No problem, ma'am. You just
clarify?
ask me through my mail. I will give my mail
Uh,
ID.
if any day
You
I
just
have
share your
one,
thoughts and
I
your
have
doubts.
some
I will
doubts.
clarify
Can
you.
you?
No problem, ma'am.
Thank you,
You
madam.
just
Thank you so much,
ask
madam.
me through my mail. I will give my mail ID.
Okay, madam. Bye.
You just share your thoughts and your doubts. I will clarify you. No problem, ma'am.
Thank you,
You
madam.
just
Thank you so much,
ask
madam.
me through
Ma'am,
my
can
mail.
you
I will
share
give my
your
mail ID.
PPT,
Okay,
ma'am?
madam. Bye.
Sure, ma'am. I will give that PPT to the coordinator, and later on they will share it.
Thank you so much, madam.
Ma'am, can you thank you, share
Thank
your
you,
PPT,
madam.
Okay,
ma'am?
ma'am. Sure, ma'am. I will give that PPT to the coordinator, and later on they will share it.
Thank you so much, madam.
Yeah, ma'am. Thank you, ma'am.
Okay, ma'am. Sure, ma'am. I will give that PPT to the coordinator, and later
Participants,
on they
any
will
other
share it.
questions?
Yeah, ma'am. Thank you, ma'am.
Okay, ma'am. Sure, ma'am. I will give that
This is a
PPT
very
to the
interactive session.
coordinator, and later
Participants,
on they
any
will
other
share it.
questions?
Yeah, ma'am. Thank you, ma'am.
Okay, ma'am. Sure, ma'am. I will give that
This is a very interactive session.
We are grateful for the
Participants, any
enlightening
other
mathematics
questions?
session.
This is a very interactive session.
We are grateful for the
Participants, any
enlightening
other
mathematics
questions?
session.
This is a very interactive session.
We are grateful for the
Participants, any
enlightening
other
mathematics
questions?
session.
This is a very interactive session.
We are grateful for the
Participants, any
enlightening
other
mathematics
questions?
session.
This is a very interactive session.
We are grateful for the Sorry for the trouble. We are grateful for the enlightening mathematics session we had today. Your presence and participate made it a truly enriching experience. A special word of appreciation to our chief guest, Dr. G. Ramya, for taking the time to share valuable insights with us. Your expertise and passion for the mathematics field inspires us all. We also extended our thanks to the organizers and volunteers to make this event a success. Thank you once again, and we look forward to many other engaging sessions in the future. Thank you, Ramya ma'am. Thank you so much. Thank you so much for all participants. And we look forward to many other engaging sessions in the future. Thank you, Ramya ma'am. Thank you so much. Thank you so much for all participants.
Ma'am, please unmute yourself, ma'am.
Sessions in the future.
And
Thank
someone
you,
was
Ramya
raised
ma'am.
their
Thank
hands.
you so
That's
much.
why
Thank you so much for all participants.
Ilangovan.
Ma'am, please unmute yourself, ma'am. Uh,
Have you any doubts, sir? And someone was raised
Please
their
ask
hands.
your
That's why
question.
Sir, if you
Ma'am,
have any
please
doubt,
unmute yourself, ma'am. Uh,
have you any doubts, sir? And someone was raised
Please
their
ask
hands.
your
That's why
question.
Sir, if you
Ma'am,
have any
please
doubt,
unmute yourself, ma'am. Uh,
have you any doubts, sir? And someone was raised
Please
their
ask
hands.
your
That's why.
question.
Mr. Ilankovan, any
Sir,
other
if you have
questions?
any doubt, I think he mistaken.
Okay. Thank you, Ramya. Mr. Ilankovan, any other questions? Thank you so much for your presence.
I think he mistaken.
Okay. Thank you, Ramya. Thank you so much for your microphone is mute, Ramya ma'am.
Yeah, ma'am. Yeah, ma'am.
Okay.
Uh,
Anything else?
Nothing. That's all.
Your
Thank you so
microphone is
much.
mute. Thank you, Ramya.
Thank
Thank you,
you.
participants.
Yeah, ma'am. Yeah, ma'am.
Okay.
Uh,
E-certificate will be provided within
nothing.
7 days.
That's all.
Participants, we will share the
Thank you,
Google
participants.
Yeah, ma'am. Yeah,
feedback
ma'am.
form to you through WhatsApp. Will be provided within now 7 days. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now 7 days. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now 7 days. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank you
Yeah.
all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session. Thank
Yeah.
you all your participants. Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session.
Yeah.
Thank you through WhatsApp. Will be provided within now. Everyone can leave. We can wind up the session.
Yeah.
Thank you all your